to locked state machine. So state machine can lock up at the start of a state, startup of state. By default, enumerated types are two state types, and the default values of the first level in the enumerated list is 0. Actually, what they're trying to say is, by default enumerated type is two state type, and default value of the first level is 0. So the functional logic based on the two state enumerated type can have gochas. You see this is enumerated type, and the value of wait is 2 tick b00, load is 2 tick b01, store is 2 tick b10. So in simulation, this example will lock up in wait state. Applying reset with 2 state or 4 state will not get the state machine out of lockup. Actually, so what is the problem is locked state machine. Sometime we know that there is locking in your state machine. How to avoid that thing? Okay. So the enumerated types are two state types, and the logic values of the first level is enumerated list 0. So you see enumerated type, wait, load and store. So this is 2 bit, 2 state. So wait is 2 tick b00, load is 2 tick b01, and store is 2 tick b10. Okay, these are the value of two state variables. Now functional logic based on two state enumerated data types can have a gochas. What they are trying to say, in this state machine, when you apply a reset, okay, when you apply a reset, what is the value of state? The value of state is wait. Okay, so but it is a two state variable, right? State, we define state is as a two variable state, right? So state is having either, so 2 tick b00 definitely, right? Because this is 2-bit variable, and when you are resetting, it will come to some known state as 2 tick b00. So already your state is at 2 tick b00, and when reset will come, your state is wait. Okay, so again you are staying in the same wait state, right? So there is no transition in this, both are in same state. So if there is no transition in this always block is waiting for transition. Okay, so this block will never execute, because initially itself when you start, your state value is 2 tick b00. When you are applying reset, again it is in same value, so there is no transition between these two. So if there is no transition, this block will not execute. But how we in Verilog it is executing, initial value of state is 2 tick bxx. After that, if you are coming to 2 tick b00, there is a transition, that's why this block will execute. So this is the deadlock conditions. Okay, so this is the disadvantage of two state variables, so we should keep this thing in mind. Okay. So that is what they are trying to say. See, when always underscore flip flop state sequence is reset, it will assign the state the value of wait, okay, which is the same value as the current value of the state. So, and thus does not cause a transition on the state, but this block is waiting for transition, so this will not execute. Since state does not change, the always underscore state combination procedural block does not get triggered, and since the combination block is not entered, next state is not updated, so there is no change in next state also. So this is a deadlock. Here it will, your state machine will work. So coming to, on the positive edge of the clock, state is assigned the value of next state. Again, when reset is removed, next state is what? Load on this only, sir. Next state is what they are trying, 00, because 2-bit, right? So initially all 2-bit variables are initialized to 00, right? So that they are trying. Next state is not updated to new value and remain in its initial value of wait. So that is what they are trying. So it does not change. So how to avoid this? So the best way to avoid this gocha is to use the system Verilog always underscore comp for combination block in this code. Instead of always at, you use always underscore comp. Unlike Verilog, unlike the Verilog, means if you are using always underscore comp, means it is not waiting for any sequence. Here it is waiting always at state. So it will, by default it will execute once, always underscore comp. Okay, so suppose initially your state is wait. Okay, by default it will execute. So when you are in wait, next state is load. Okay, so always underscore comp block will always execute once by default. So after that any variable change, then so you can avoid that thing. So they are telling always under will automatically execute once at a time 0. Okay, and even if the sensitivity list was not triggered. So you can avoid this thing with the use of always underscore comp. A second method to avoid these things is to declare the state and next state enumerated as a 4-state variable type. So they are telling instead of 4. So initial value is xx, and when reset it will come to 0. So there is a trigger x to 0 transition. So this will see that transition and this will execute. A third fix. This two-state log gocha is to explicitly assign the value of wait, load and ready that are different than uninitialized value of the enumerated variables. For example, what they are trying to say? Oh, they are assigning the value is 2 tick b01, 2 tick b10, 2 tick b100. So initially state is 000. When reset it will come to wait state. So wait state there is a transition 001, right? So by seeing this transition, that current state will execute. Clear, sir? So in this way this is. So they have given 3 fixes. Instead of assigning this thing to 0, you assign it to some transition value 1. So this was about two-state. Okay. Now hidden design problems. So design error might not propagate through two-state logics. So they are telling errors are not propagating. We'll see how. An important gotcha to be aware of when modeling a two-state data types, whether at RTL level or verification level, is the fact that two-state type begins simulation with the value 0. So this is the key instead of x. So it is common for a value of zeros to also be reset value of the register within the design. So data reg, initially it is 0. So as soon as reset will come, again it is 0. Okay. So when neg edge of reset will come, data in, where is the data in? Okay, we'll see what they're doing. The initial value of data reg is 0 here. Okay, this is also the value of data reg is reset. At reset time also data reg is 0. So this means that if for some reason the design fails to generate the reset, it will not obvious by looking the value of data reg that there was a failure in the design logic. You got, sir? Actually the problem is, suppose you want to verify the reset. Okay, how you will verify reset? When you are applying reset, everything will come to 0 state. Okay, already there is a 0 state. Then even after reset this is 0 state. Then how you will come to know? If you are assigning data reg as 1 here, and after that you are applying reset, then you are coming data reg to 0, then you can say that your reset is working. So here you cannot ensure that your reset is working or not, or you are getting reset or not. Even that you cannot ensure. So another way in which two-state logics can hidden design error is when the operation return a logic x. So if you so we know that two-state variable only 0 and 1 possible combination is there. Suppose x you are comparing with unknown. Okay, so it will return either 0 or 1, not x. So how you will find that you have compared with unknown value? So that is the problem they are telling us. Module bit equation input a and b. Now they are comparing a equal to b. In the above example, the gocha is a two-state input. What will happen if there is a design error and either a or b input is left unconnected? Okay, with the 4-state values, the unconnected input would float to a high impedance. So because 4-state variables, all the 4 possible combinations there, and if a equal to b operation will return a logic x, an obvious design failure, right? So if it is a 4-state variable, it will return x and will